I'd like to take a few minutes to walk through some UXR measurements where the UXR is under the control of the vector signal analyzer software. We'll use the BHQ pulse option and the advanced radar option. Let's make some measurements. Let's first look at a measurement of a simulated radar echo pulse and a jammer pulse. These are both at 10 gigahertz, 1 microsecond wide. I'm sampling at 128 gigasamples per second with a 33 gigahertz bandwidth. I'm at 2 millivolts per division. And what you'll see is that this small radar echo pulse, which is at about minus 65 dBm, is barely discernible. The minus 45 dBm jammer pulse, pretty easily visible. And what we're going to walk through are some steps where we're able to make accurate measurements on both the radar echo pulses as well as the jammer pulses. Now what we're going to do is use the vector signal analyzer software to put the UXR oscilloscope into a mode where it's using real-time digital down conversion. That's going to take that 128 gigasample per second time volt data and convert that into much lower sampled IQ data, sampled just fast enough to be able to discern this modulation that's on top of these pulses, and that these pulses actually are creating versus it just being a carrier. And then we're going to process that information where we're only going to be putting into memory the IQ samples where we have pulses present. And that really allows us to maximize the use of the memory on the oscilloscope and then pass that sampled IQ data off to the vector signal analyzer software where it can apply all kinds of measurements. So let's do that. So I'm going to scroll down here. We're going to bring up the VSA software menu, and then I'm going to press run, and we're going to look at some different ways that I can adjust the span of this measurement, and you'll see the difference that it makes in the measurement. So I'm going to hit run. These are these same exact two signals, except now, as I mentioned, we're using the real-time digital down conversion, and I'm tuned to 10 gigahertz. I have a span of 2.16 gigahertz, which is much less of a frequency range, so lower noise than when I had 33 gigahertz. But the pulse, this minus 65 dBm pulse, is still very noisy. Now watch what happens as I bring down the span, and this happens to be a pulse with a 40 megahertz linear FM chirp. So here we are at 2 gigahertz, 1 gigahertz span, 500 megahertz, 200 megahertz, 100 megahertz, and finally 50 megahertz span. Okay, this completely has changed the noise floor of this measurement, and that minus 65 dBm signal is very easily discernible, and in fact you can make good measurements on that. And that's kind of the next step, is we can go and use the BHQ pulse option to be able to apply measurements. I'm also going to turn on the real-time digital down conversion plus the variable length segmented capture. And what that's going to do is it's going to not just measure these pulses, but apply a whole host of measurement parameters to it. Okay, so here we see these small radar echo and large jammer pulses being pulled into segments. Okay, and depending on how close together they are, they may go into one segment, they may get their individual segments, but the scope's making a decision for how to efficiently pull this information as IQ data into memory and then allow measurements to be made. So here we see, for example, the first pulse being measured, minus 64.41 dBm, and there's a whole host of measurements on this, including things like it's 1 microsecond kind of width. It has a PRI, in this case, of 2 microseconds. That's showing the spacing that was happening between these two pulses, and you can see the kinds of measurements that are being made on the pulses. I can also display things like the linear FM chirp that's occurring on these two pulses. And now in this case, I have set this up for the capture so that I'm just pulling in a small number of pulses. Here's 10 pulses, and using the variable length segmented capture. And I'm also using this so that I've made the pulse detection to be 23 dB down from the max signal level. Well, that lets me get down into this range where I can be triggering initially off of this minus 65 dBm pulse, and then have a threshold, detection threshold, that finds these pulses and allows me, well, the trigger level threshold allows me to define where I'm going to sense that pulses are there. The detection threshold is going to apply a determination of pulses for measurement. So, and you can see here in this case, I've got a couple of these pulses that are being highlighted as being made for measurement. Okay, and if we look here in the time, this shows you that my sample rate is 64 megahertz to achieve a 50 megahertz span. And that's fine to be measuring these 40 megahertz wide linear FM chirps. And then I've selected to look at a couple of pulses here. I could change this. I could make this, let's look at the first 6 pulses, for example. It's really whatever you want to do there. What I am going to do, though, is going to ramp this up a bit. Let's say we want to look at 100 pulses. And let's say that we want to capture up to a couple hundred segments. And now I'll hit run again. And this time we should see a significantly larger amount of time over which pulses are being captured. And then I'll have a pulse table that's going to let us see what's happening. So here we go. You can see the pulses here up through the 100 that I asked for. You can see how these are going from the small radar echo to the large jammer. And if we look at the rise time edge and back this up, we could also be able to see where were these pulses located. Here's the first pulse. It was at 3 microseconds out relative to the first. Yeah, that's what we're seeing here. And then we've got 100 microsecond PRI, and that process then repeats as I go down through. So this is an example of showing how we can capture many pulses over significant amounts of time by using the variable length segmented capture combined with the real-time digital down conversion. The next measurement is one that allows you to look at the settling time when you have a source that's changing, that's hopping in frequency. We have a source here that's hopping back and forth around 1 gigahertz. And let's take a look at how we can pretty accurately measure what that settling time looks like. So I have the signal plane. It's coming into channel 2 of the oscilloscope. I've recalled a setup that I made here where I'm actually driving channel 3 of the scope into the VSA here, and I have acquisition time, the spectrum, a pulse summary. We'll have a table showing us pulses, and then I'll be able to look at both amplitude measure time and FM measure time. This is the key place we're going to look because it should plot out the frequency as it changes, and then we can look at that time and apply an automatic measurement to it. So let's go ahead and make a capture. I'm going to come down here and I'm going to say Autoscale. So here we see the signal. You see it up top here, that line, little bitty squiggles in amplitude when there's a shift in frequency. You can see this, it's centered at 1 gigahertz, span of 50 megahertz. So you can see that's hopping back and forth over about 40 megahertz. And then if we take the select area tool and look carefully between pulses 1 and 2, or I'll call it regions 1 and 2, now we can see this change in the frequency as it transitions from the lower to the higher. And we're making measurements that are looking at the distance between the regions here. You'll see that it's around 29 microseconds. This is going from the minus 20 megahertz to plus 20 and then plus 20 to minus 20. You see what those transition times look like. But let's do a little verification using some markers. So I think what I'm going to do here is I think I can grab the markers that we've used from before. I'm going to take this one and drag it over. Oh, I think it's off screen, so I think what I'll do instead, let's take a marker, let's right click, let's hide all the markers, let's place a marker here, and then I'm going to zero delta that marker. Then I have a second marker that I can just put here. And 1 delta 2, we see that 28.8 microsecond kind of measurement that matches right up here with what we're seeing in the automatic measurements. So this is a way to be able to look at that settling time on a CW signal. So there's really nothing in amplitude to trigger on, yet I'm still able through these measurements to be able to make some automatic measurements on the transitions. In the next measurement, I'm going to create pulse-on-pulse signals using the VXGC signal source in its ARB mode. This has been loaded up with a number of IQ files. For example, this is a 1 microsecond wide pulse, 20 microsecond PRI, 10 megahertz width, and you'll see it's offset by 1 gigahertz from the center frequency for this particular physical channel. Each physical channel of this source can have 8 virtual channels, which can be 8 emitters, pulse on pulse or pulse on signal. You'll see here I've got 6 of these pulse signals. I can also add in a QAM 128 COM signal, that's CW. Here's a multi-tone signal that's also CW. But for right now, I think for this measurement, we're just going to use these 6 pulse on pulse signals. And so let's now move over and observe the oscilloscope. Okay, so we're just going to start off looking at both time domain and frequency domain for channel 1 of the scope. So here's where we see the 1, 2, 3, 4, 5, and 6 microsecond wide pulses that are pulse on pulse in the time domain. And you also see the 10, 20, 30, 40, 50, and 200 wide linear FM chirp signals in the frequency domain. Now, this is very difficult to try to make pulse measurements on, especially automatic measurements. But since these emitters are at different frequencies, we could tune each of the 4 channels of the oscilloscope to these signals. We just need to feed the output from port 1 of the signal source through a splitter out to each of the 4 inputs of the scope and then tune each of the channels. To do that, we use the VSA software. Now there's 2 stages I can show you with that. If we go back to the VSA, and let me recall a measurement, file, recall, setup. So what I've done now is turned on the real-time digital down conversion. I'm not using the variable length segmented capture, but I am tuning to a frequency, 11.25 gigahertz. I've got a 2.1 gigahertz span. I'm able to see that same kind of FFT view as I did with the oscilloscope by itself, but the difference now is I've got much lower noise because I've tuned down that span. I'm working now with IQ data, and that allows me to bring that over into the VSA software and have very fast kind of response. And we also have this waterfall display. The next thing I'm going to do then is turn on the advanced radar, where I can tune each of the 4 channels of the scope to this, and this. These 10, 20, 30, and 40 megahertz wide linear FM chirps, and be able to separate those and do pulse parameter measurements on them. I am tuning each scope channel to each center frequency of these sources, and then applying pulse parameter measurements to those pulses to be able to fill up pulse tables for each of the channels and give us a sense for what these look like. So I'm going to go ahead and hit run. You'll see, okay, I'm going to hit pause. You'll see, well, I guess we can let it run for a minute. You'll see it's a pretty fast response because we're using the real-time digital down conversion. We're also using the variable length segmented capture. So it's pulling these pulses into these individual segments. You'll see the 10, 20, 30, and 40 megahertz wide linear FM chirps. These pulses you can see that are being measured here. If we look across, we should see the different pulse widths as these are being separated out by each channel, tuned to them. There's your 1 microsecond wide, 2, 3, and 4, and here you see the linear FM chirps on each one of these. Now then you certainly could go ahead and pump up the number of pulses, number of segments to look at a lot of these signals happening over time. But this gives you an idea how we were able to take those signals that were pulse on pulse in the time domain, and by virtue of them having different frequencies, tuning to each one and being able to fill up the pulse tables. This is using the advanced radar feature. The next measurement I'd like to show you is that of angle of arrival. Here we're seeing signals coming in on ports 1 or channels 1 and 2 of the UXR, and you'll see as the sources are simulating the change of phase between the carriers on these 2 simulated signals as if they were being received on a couple different antennas, and so a radar warning receiver could take that delta phase information and turn that into either azimuth or elevation information as far as the direction of that signal and where it's coming from. All right, well, what we can do is feed this into the VSA software and be able to actually calculate out what is that azimuth. In this case, we're going to have a couple antennas being simulated as if they were side by side, 1 lambda spaced. So let's go to the VSA software and let's hit run. And what you're going to see is a capture of the, let's shrink this down. Whoops. Capture of the pulses here. There's your spectrum, centered at 3.5 gigahertz. It's making pulse parameter measurements on that signal. Here you can see some of the parameters being measured on that signal. It's about 1 microsecond wide. Here we see the azimuth being plotted out as the signals are changing phase between the ports and being converted into degrees of azimuth. So this makes for a very easy way of just checking to see what kind of condition those signals are in and if they're what you're expecting. Now, some of the setup for this, if we go into pulse properties and analysis, we see under here the angle of arrival, and in this particular example we have 2 antennas that are horizontally spaced. They happen to be 1 wavelength apart at 3.5 gigahertz. You could have also selected what number or fractional part of a number or multiple wavelengths you want the antennas to be separated, and then you can choose either delta phase or time difference of arrival for the calculation, in this case, of the azimuth. If you had a different antenna pattern, for example, if you had used 3 antenna L-shaped or 4 antenna square, then I could have your multiple ports to be able to determine both azimuth and elevation and plot both of those into the window. So that's an example of using the UXR oscilloscope with the VSA software to do angle of arrival measurements. The next measurement we're going to look at is pulse train scoring. We've done things where we're looking at individual pulses and making pulse parameter measurements, but this is going to look for trains of pulses. Let me explain. So what I can do is define under the analysis for train scoring trains of pulses. For example, train 1, I could say, is when I have 3 pulses with these kind of parameters, and specifically I've checked the width and PRI and said these are the scoring metrics as far as how much tolerance on the numbers I have up here. 2 microsecond width, 20 microsecond PRI. I want to see 3 of them with 20 microseconds, then 3 more that have 25, and then 3 more that have 30. And if I see these 9 pulses happen in a row with these characteristics, then I'm going to call that train 1, and I'm going to mark it that way and allow it to be something that I can identify as I'm making measurements. Similarly, I've defined a train 2 here, which is a pulse that has 2 microsecond width with 10 microsecond PRI, train 3 with 2 microseconds and 80 microsecond PRI, and finally train 4 with 2 microseconds and 4 microseconds PRI. Now you can see there's a lot more factors we could have tied into this to make the definition of the trains. This is just a super simple kind of example. All right, so what we can do then, I've set up signals that are playing these kinds of pulse patterns that we should be able to identify. And so I'm going to hit run. This is going to be a single sweep. All right, so there we go. It has captured a chunk of signals, and this is the basic pulse table that you see. Here's your pulse train search table, which is identifying then what kind of trains we're seeing. So in this, and one thing I'm noticing here is that I saw only 7 pulses where I would have needed 9, or I guess I saw 5 here, didn't I, in order to be able to call that a train. All right, so that makes sense that these first pulses, even though they had 25 and 3 of them that were 30, I didn't see that entire sequence of 9. Okay, that's fine. Then I start seeing a bunch of pulses here that have a 10 microsecond PRI. Each of those you'll see are getting scored for train 2 very highly as matching train 2. They're highlighted in blue here as well as here. Then we see 5 pulses coming through with this 80 microsecond PRI. Those get flagged here as very high probability that these are in fact that train. And then finally train 4, where I have these pulses coming through with a 4 microsecond PRI. If we scroll down, you'll see there's actually one pulse between pulse train 4 and identifying pulse train 1. It has a 100 microsecond PRI. It doesn't match anything that we had. And then here we see where I actually pull in 9 of these pulses, 20 microsecond PRI, followed by 25, followed by 30, and those get flagged as pulse train 1, and so on. So you get the idea of how this works. And so it's very handy in terms of being able to discern not just pulses, but pulse trains that might be representative of a certain kind of a condition. Now, one of the things that's nice about this is under measurement setup, pulse properties, and under analysis and the train scoring, I don't have to enter all of this in manually. For example, I could say, I'd really like to define the pulse train 1 to be between pulses 42 and 50 of what I saw here. And actually starting off, you would have started here like this and identified 41 through 50 has this sequence of PRIs right here, the 20 followed by 25 followed by 30, and I say, you know, I want that to be a train. This is before maybe I set up anything. And I could say then, if I pull back up this measurement definition, I could say, so I guess I just wasn't being super careful at looking. So 42 through 50, copy measured pulses. There. Okay, so there's our 20, 25, 30. I can see over here where that definition of train 1 is actually being detected from the data that we have in there, and I didn't really have to enter in all those values. I was able to just measure signals that I brought in, that I felt met a condition that I cared about, and assign that to one of the pulse trains. Final example I'd like to show, and I'm just going to use a demo example here, recall demo, under our pulse functions, and that's of identifying emitters. Okay, so if we go in here, we can bring up ones called pulse de-interleaving, and if we open that up, you know, often you'll have multiple emitters that are being captured together, and it can be a bit difficult to try to discern what's there, the different PRIs and so forth. And here's an example where we've got 3 different pulse trains that are happening, but I'm able, by having defined under pulse properties and under analysis, in this case it is de-interleaving, how each emitter has certain characteristics, like frequency, upper and lower frequency, amplitude between a range. You can choose what kind of modulation. You can see the many different possibilities here. And then if it meets these conditions, it's going to put those into these bins of which emitter. So in this case, I've defined 3 different emitters, and you'll see how these are being flagged over here. In fact, if I stop this and I press emitter ID number, you'll see how these 5 pulses were found. Notice their starting point, 0, 100, 200, 300. They've got 100 microsecond PRI. Here are other pulses, 50, 150, 250. They've got 100 microsecond PRI, different frequency. And then finally, this third set. And notice they all have different amplitude ranges. So this is a way of being able to separate out multiple emitters that are all captured together, and to be able to do pulse analysis on those, and to be able to easily recognize those. So we've seen how the UXR oscilloscope, working together with VSA and features like the BHQ pulse option or the advanced radar option, is able to, one, use real-time digital down conversion to let you tune to a frequency per channel with a span, greatly reduce the noise, and also change that into IQ data, which is a much more efficient kind of sample rate designation or representation of that signal that you're receiving. We had the variable length segmented capture, which let us put the pulses into segments and to really reduce the amount of time just capturing noise and concentrate most of the IQ data going into memory, being where the pulses are actually located. That allowed us to measure many pulses over larger amounts of time, which might line up with some of the scenarios that you're interested in. We also saw how it was possible to look at the transition time, settling time, when I was having frequency hopping, even on a CW signal where the amplitude remained constant. We looked at how I could measure angle of arrival by changing the measured phase shift between a couple signals on the 2 ports coming into the UXR oscilloscope, and then plotting that as azimuth or elevation, or both, depending on the number of ports that you were using for the angle of arrival. And that could be difference in phase, interferometry, or it could be time difference of arrival. And then we also saw some ways that I could look at pulses from a pulse train perspective and define the way different sequences of pulses, if they happened, you want to call that a certain pulse train, identify it, colorize it, make it where it's able to be looked at in these tables and separated from others. And then finally we saw how we could define what would constitute emitter 1, 2, 3, and highlight those in color and be able to let you separate out those emitters so you can more easily look at their pulse parameters. So hope that gave you a good idea of some of the kinds of things that you can do with the UXR oscilloscope together with VSA, especially in the area of radar and EW kinds of pulse analysis. And if you'd like more information about this, please contact your local Keysight representative. Thanks for your attendance.